Okay, so now we are going to get a more in-depth look at line integrals, and one that is slightly more mathematically rigorous, though not that much more mathematically rigorous. So let's start by saying that we have some curve. So let's say that C is a curve with smooth parameterization R of t is equal to x of t, y of t. Okay, and remember the smooth part just means that we can take derivatives of the component functions and that the derivative, in other words, r prime is never equal to 0. Okay, that's what smooth means. The smooth, again, just means that we can take derivatives, x prime of t, y prime of t, and that r prime of t is never the 0 vector. Okay, so let f be a function defined on C. Then the line integral of f on C is the following. So the line integral, this is the notation, f ds, so this C is the curve, so that means we're taking an integral over a curve of the function f with respect to what's called the arc length measure. Okay, this is equal to the limit as n goes to positive infinity of these following Riemann sums. I equals 1 to n f of xi, yi, delta si. Let me just briefly identify what these things are. So it's going to be very similar to the last video. So let's say we have a curve here in the xy plane. So some curve like this, okay, it has smooth parameterization. This curve is given by the parameterization r of t, and we know that t is in between a and b. Okay, so we're going to break up t, break this interval up. We're going to divide the interval a to b into n equal sized intervals. I don't know why I put a hyphen there, that's not needed. We're going to divide this interval into n intervals of equal size, of equal length. And the length will be delta t. Okay, so for example, this point right here is r of a. This point right here would be something like r of a plus delta t. This point right here would be something like r of a plus 2 delta t. And the idea is that even though the intervals, the time intervals or the t intervals are in equal lengths, that does not mean that the length from here to here and here to here are equal. So for example, it could be that this point right here would be given by r of a plus 3 delta t. Okay, and so then the xi's and yi's, so the point xi, yi, this is going to be r of a plus I delta t, and delta s is going to be equal to the square root of x I plus 1 minus xi squared plus yi plus 1 minus yi squared. Remember, we saw in the video that this quantity is roughly equal, each one of these quantities is roughly equal to the arc length that connects the 2 points. So for example, if this is xi, yi, and this is xi plus 1, yi plus 1, then what we're saying is that this arc length right here is approximately equal to this formula. Okay, and another way to see this that we saw in the formula before is this is the square root of delta xi squared plus delta yi squared. Okay, and this is what delta si is. Okay, so now the idea is as we divide, when we take smaller and smaller subdivisions, in other words, as n goes to infinity, delta si is going to go to the actual arc length of this, and this is going to approach a certain integral. And we want to be able to write this integral in terms of an integral that we can actually compute without having to do Riemann sums. So the idea that we want to use, let me get this erased, is that we know we have a formula for arc length. Okay, so we know that we have this arc length formula. S of t is equal to the integral from 0 to t of r prime of tau d tau. And so we saw before that this means that ds dt is equal to the magnitude of r prime of t. This is just the fundamental theorem of calculus. So what it means is that ds is equal to r prime of t, the magnitude of r prime of t dt. Okay, and we're going to use this to help us compute this integral, to help us write this integral as an integral in the variable t. Okay, so this is going to be the integral from t equals a to b of f of r of t times ds, which is r prime of t, the magnitude of r prime of t dt. And another way to write this is the integral from t equals a to b f of x of t y of t times the square root of x prime of t squared plus y prime of t squared dt. Okay, so in practice, to compute a line integral, we use this expression right here. And in the next video, we will actually compute a few line integrals, do a couple of examples to see how all of this works.